Okay, thanks people joining. For all the students who are registered in Colloquium, the last summary is due on Friday. So I see some of you have submitted already, but if you have not, please don't forget. So that's the announcement I had to do, and I'll let Deepak introduce the speaker.
Hello, everyone. Welcome to the last colloquium of the semester. It's a pleasure to introduce Professor Dr. Christoph Weidenbach. He's from Max Planck Institute in Saarbruecken, Max Planck Institute of Informatics, where he's been there for a number of years. He got his PhD from University of Saarland, if I remember correctly, in 94 or 95, working on the sparse system. Actually, I've known him ever since then. And he's done a number of things. Currently, he heads the automated reasoning group at Max Planck Institute, and he might be heading the largest group in automated reasoning in the whole world on that particular topic. And he's published extensively on a number of topics, including protocol analysis, of course, automated reasoning, superposition-based theorem provers. And he's been currently thinking a great deal about how to combine conflict-driven clause learning with first-order reasoning. It's a pleasure to have Chris. Chris, floor is all yours.
Okay, so thanks a lot, Deepak. So yeah, I'm sitting in Germany, right? It's 10 o'clock here, 10 p.m. local time. You see in the back, it's already, everything is prepared for Christmas, right? I'm sitting in the lobby of a hotel where I stay on Wednesdays with a glass of wine, so cheers. So I will try to explain a little bit what is needed designing algorithms for hard problems. So at any point in time, if you have a question, please interrupt me. Feel free to speak up or raise your hand or whatever. I will have a look in the chat, right? So don't hesitate to interrupt me. Okay. So yes. So what is computer science about? One way of looking at computer science is, of course, to say what we want to do is we want to solve problems with the help of a computer, right? And design algorithms that eventually run on a computer that solve problems. Now, for this talk, I will make a very, very crude separation of problems that can actually be solved between tractable problems. This is typically the type of problems where algorithms people look into, right? And typically, these problems only need polynomial resources to be solved, time, space, whatever, right? So, and the typical example that is part of any, at least in Germany, part of any bachelor study is that you look into algorithms that sort arrays or things like that. Another example is if you have a graph and you want to find the shortest path, right? For these problems, you can have very, very efficient algorithms. And on the other side, there is hard problems. And what is characteristic for hard problems is that they may need exponential resources. So typically, at least worst case, they need exponential resources, right? And the classical problem here is propositional satisfiability, right? We want to figure out whether a set of propositional clauses has a model. But actually, any problem of hard or software verification or analysis is a hard problem. But also any real-world optimization problem is a hard problem. So hard problems are actually ubiquitous in the real world, right? And for many years, it was believed that hard problems cannot be solved. For example, Donald Knuth believed for a long time that it doesn't make sense to look into hard problems. But this has changed around 20 years ago. And this talk is a little bit about why it changed and what are actually the prerequisites that are needed to solve hard problems in practice. Okay, so but let's start a little bit with some tractable problem. And the tractable problem I wanna study is simply sorting some array of integers, right? So here is some array of integers, right? 8, 6, 7, 1, 5, 4, 3, 2. And let's assume we want to sort this in ascending order, right? And there are a number of very well-known algorithms how to do that very efficiently. And one is that you simply split this array into 2 arrays and then into 4 arrays until you only have arrays of size 2. And now you order your arrays of size 2, right? You can now get 6, 8, 1, 7, 4, 5, 2, 3. And then finally you merge these split arrays back, right? So we first get 1, 6, 7, 8 for the 2 pairs on the left, and 2, 3, 4, 5 for the 2 pairs on the right? And eventually we also merge these 2 arrays and at the end of the day get the sorted array, right? And this is one of the very well-known algorithms for sorting arrays. Sometimes even one of the most efficient ones, depending actually on the current structure you have at hand and on the problems you have at hand. And it's very well known as merge sort. And this is kind of divide and conquer strategy, right? You divide the problem into smaller problems, you solve the smaller problems like the pairs, and then you put it back together to the overall problem. It works top down, and it has very low complexity, so it's n log n. And nothing needs to be learned to solve this problem, right? This algorithm will always work on any type of array. It doesn't look into the array. It does not know anything about the numbers that are actually in the array. It will just work on the structure of the array and solve it. It does need almost no extra resources. Actually, it needs, of course, a little bit of extra resources to do the splits. But at least the amount of resources it needs is fixed, right? It's fixed by the input. And in contrast to this, all these tractable problems, right? And here is another tractable problem that is the shortest path in the graph that you might also know, right? And in contrast to this are hard problems. Now for tractable problems, there's a rich theory, also background theory, right? There are general approaches how to attack these problems like divide and conquer, dynamic programming, and so on. And typically these algorithms are designed in a way that no knowledge about the specific problem instance is needed, right? Our merge sort runs on any area of integers without looking into the integer and always runs exactly the same way. Very important, there are no extra resources needed, in particular no dynamic resources, right? You just know the size of the initial array and then you know what to do and what will happen. And it's purely analytical, right? It simply divides this array into smaller chunks, looks into the chunks, sorts them, and then puts it together. Now, the lessons that was learned in the past, I would say 60 or 70 years, that such an approach is not sufficient to efficiently solve hard problems. Now, efficiently solving hard problems is a kind of contradiction. So what is meant here is that you get to a level of solving hard problems that has an impact in practice. Okay. And the classical hard problem I will use to introduce the techniques that have been developed in the past 70 years with some breakthroughs in the past 20, 25 years is propositional logic, in particular propositional satisfiability. So in propositional logic, and I assume you all know about propositional logic already, you have these variables that we might call here A, B, C, P, Q, R, or whatever, right? And then here we restrict to only a subset of well-known logical operators because we are only interested in clause normal forms. So we are perfectly fine with logical AND, logical OR, and logical NOT. And then from this we can build formulas, and the only kind of formulas we are interested here in is what called the clause normal form. It means a conjunction of disjunction of literals, right? So here we have A or B, which is what we would call a clause. It is junction of two positive propositional variables A and B. And here we have not A or C of two propositional variables A and C, and not A is of course the negation of the atom A. Okay, when propositional logic comes with a very simple notion of truth. So it basically says, okay, one may assign to any propositional variable either true or false, which we denote here by 0 or 1, right? And then we can define what this means to the operators. So for logical AND, a conjunction is true if both arguments are true. We are actually 1. disjunction is true if at least one of its argument is true. And of course, a negation flips just the truth value of its argument, right? Good. And then we have what is called evaluation that actually assigns to all propositional variables true or false, that means 0 or 1. And once we have such evaluation, we can check whether it satisfies a CNF, a set of clauses, or a conjunction of clauses or not. For example, here, what we have is that A is assigned false, is assigned 0, B is assigned true, C is assigned true, it's 1. And actually this satisfies these two clauses here because the first clause A or B is satisfied because B is true. And the second clause, not A or C, is satisfied because C is true. So propositional logic is well known since the mid of the 19th century. But the question is how can we actually then check whether such a set of clauses or conjunction of clauses is true? And the simplest way always to do that is use the semantics. And the semantics for propositional logic is truth tables. And truth tables are simply a systematic way of enumerating all potential valuations, right? For example, here we have again three clauses, P or Q, not P or R, P or not Q. And here's a systematic enumeration of all valuations of P, Q, and R. And then we can check whether these clauses are satisfied or not. Yeah, so to the left of this truth table, we have the three propositional variables, P, Q, R, right? And then we systematically generate all the potential truth values for these variables. And then we can systematically bottom up figure out whether the disjuncts are true and eventually whether the overall conjunct is true. For example, if P, Q, R are both 0, then of course P or Q is 0, not P or R is 1, P or not Q is 1. But of course, the overall conjunction can only be true if all three clauses are true and 0, right? So at the end of the day, we might figure out, for example, that if P is 1, Q is 0, and R is 1, then of course P or Q is true, not P or R is true, P or not Q is true, and actually the overall conjunction is true. So actually this means this conjunction of disjunctions with CNF is satisfiable. The issue here is that in general, of course, for n propositional variables, there are 2 to the n such valuations, right? And we all know if something has exponential complexity, we can only solve small instances on a computer, right? And what is really ugly here is that if this formula is not satisfiable, if you use truth tables to check it, it means you will go through all these 2 to the power 2 to the n valuations, right? So for sure, truth tables are not a nice idea, are not a good algorithm to check whether such a conjunction of disjunction, such a CNF is satisfiable. But this was actually the state of the art for a pretty long time. And there are many issues with that. One is that nothing is learned, right? If we have figured out here that if P is 0, Q is 0, R is 0, the formula is not true, we don't learn anything about it, right? So what we do here, we don't learn anything, but also we don't need extra resources, right? We simply could have a simple recursive algorithm that enumerates all the valuations. And of course, it's again purely analytical, almost like the standard algorithms for tractable problems like the sorting. Right. But for sure, there is no way you can solve a larger problem using truth tables. You cannot figure out. Good. Now, if you look at the state of the art, and I will just give you a very toy example, that is Sudokus, you will see that we can actually solve large problems. So, for example, if you look at a 4 times 4 Sudoku, so I assume you all know about Sudoku. It means you have these squares here, and in each column, row, and subsquare, every number has to occur exactly once, right? So for example, here there are 4 numbers given, right? And here is the solution where all the values from 1 to 4 occur exactly once in each column, in each row, and each subsquare, for example, like the subsquare here. Okay, now you can actually translate the issue of or problem of solving a Sudoku into a satisfiability problem for propositional logic, right? And the idea is pretty simple. You say for each square here and each value, I introduce one propositional variable. Yeah, you say PIJV means actually column I, row J, the value is V. And once I have done this, I can actually, first of all, encode the given values. So for example, here I can say 1, 1 has value 3, which is actually the square here. Or 4, 1 has value 1, which is actually 4, 1, 1 is actually the square here, and so on. But also I can easily encode the constraints that are needed to fix the potential solutions to the Sudoku, right? For example, I can very simply express that in column 1, this column here, there's only 1, 1. Because what does this mean? It simply means it cannot be the case that in square 1, 1 is a 1 and in square 1, 2 is a 1, right? And I can do this for all the combinations, for all columns, for all rows, for all subsquares. And at the end of the day, what will happen is that for a Sudoku of side length n, in our case here 4, we need n to the 3 to the power of 3 many variables and also formulas. So it gets polynomially, but already reasonably large. But if you give this to a state-of-the-art solver, it will be able to solve this on a 64 times 64 Sudoku. So not the 4 times 4, not the 8 times 8 that you can find at least in German newspapers. It will solve a 64 to 64 in below 1 second, right? Now 64 to 64 means you have already more than 200,000 variables, propositional variables, right? We are talking here more than 200,000 propositional variables. So truth tables are for sure not an option, right? So there needs to be something else to make this work, right? And for the rest of the talk, I will give you some of the main ingredients that have been developed in the past 70 years that actually allow now today such solvers to solve such problems and also relevant problems in practice very efficiently, and also in a very robust and predictable way. Okay, one of the first contributions to getting beyond truth tables, sorry, was done actually by Martin Davis and Hilary Putnam and Loveland. And so the idea here was actually not only to stupidly enumerate all valuations, but as soon as you have fixed a propositional variable inside a valuation, you check whether the truth values of other variables are forced if you want to have a satisfying assignment, right? So let's go back again to our three disjuncts here we have seen before for the truth table, right? And here's again our truth table. And now instead of just blindly enumerating the valuations, we could simply start with fixing p to 0, okay? So we fix p to 0, make p false, and now we ask ourselves, what happens if we fix p to false? Now, if we fix p to false, then of course, because of this disjunct here, it means we are now forced, if we want to find a satisfying assignment, to make q true, right? On the other hand, we also already see here, if we fix p to false, we have to make also q false. So in summary, this means we have to make q true and false, and of course, this cannot work. So this means already there cannot be any satisfying assignment that makes p false, right? And so that means from the very beginning, just by looking at this simple value, we can already rule out all these assignments. So if you apply this, if you add this to a simple enumeration of all valuations, you already save a lot of assignments, right? But still, you don't get an algorithm that is robust or can solve anything in reasonable time. Then independently, and actually on a completely different branch of research, in particular for first order logic, the resolution principle was invented around 65. And the resolution principle that was actually invented for first order logic, an inference principle, says the following. So if you have mapped to propositional logic, if you have here two disjuncts, right, P or Q and P or not Q, and these disjuncts contain actually literals with opposite sign, right, like the Q and the not Q here. When we cut, can cut actually these literals out, because they cannot be true at the same time. So we can be sure in this case here, P or Q and P or not Q, we can conclude that P must be true for actually these two disjuncts to hold. Okay. And resolution was a kind of breakthrough in first order logic. And it was also then studied very often and quite deeply by a lot of theoretical computer scientists with respect to its power. And one of the interesting results that came up in 1979 was, okay, if I do resolution proofs in propositional logic and do these DPLL style proofs, that mean these advanced truth tables to talk about, then there are sets of clauses, there are clause sets where resolution proofs are exponentially shorter than these DPLL proofs, right? But not the other way around. That means resolution can polynomially simulate DPLL, but not the other way around. Okay, so this might suggest actually that resolution is a good idea for solving propositional logic problems as well, right? However, this does not work. And the reason is more or less that if you think of resolution, that means combining clauses through cutting out literals of opposite sign. Basically, what you can generate is 3 to the power of n different clauses, right? Because for each propositional variable and each disjunct, either a propositional variable appears positively, or it appears negatively, or it doesn't appear at all. That means you have 3 choices for n variables. That means if you have disjuncts of length n, you have something like 3 to the power of n different clauses that you may generate. And this is, of course, worse when looking into 2 to the power of n valuations, right? And even worse, you can even generate things that are not useful at all. For example, here, right, in a similar example, we do a resolution step between not P or Q and P or not Q, when we even generate a tautology. And in this context here, tautologies do not contribute at all to any problem solving or finding evaluation, right? So we are completely useless. So it's really the case that if you apply a resolution in the propositional logic setting, it's in practice, that means if you run it on some benchmarks, it's even outperformed by truth tables, in particular if you do these tricks by DPLL, right? And it's even worse also because your truth table algorithm only needs exponential time, right? Because it enumerates all these valuations with exponentially many variations. But the resolution is even worse because you have to store these clauses. That means you even need exponential space, which is also, this is very, very bad on today's computer, because it simply means you slow down the computer ad infinitum. Okay. Then a major breakthrough was actually to combine resolution and with DPLL style enumeration of valuations. And this was actually done by 2 groups, one in Spain, one in the US, around 2000. And it's called CDCL, for context-driven cross learning. So the idea is, the basic idea is, at least from today's perspective, actually this algorithm was found by experiments. People experimented a lot, producing algorithms that attacked such problems, right? But from today's perspective, you can view it as a combination of this DPLL style enumeration of valuations and resolution. Actually, you use the valuation to guide resolution steps. And you will see in a second that this makes an incredible difference. Okay, so let's again have our running example. Let's again have a look at our truth table. And let's again have a look at this DPLL idea where you start making P false, right? And again, right, we know that this leads to a contradiction, and it cannot be that this satisfies the eventual 3 disjuncts or the overall formula, right? Now, another way of doing this is that we build this model as in a kind of stack-like way, that we simply say here, okay, let's make p false. That means we assume that not p is true, and we assign with a 1 saying that, okay, we guessed this one, right? We guessed this one. This is like in DPLL. And now, as soon as we guess this one, for example, because of a first clause here, again, like in DPLL, we know we have to make Q true. Now, this is not a guess. It depends on the not P. This is not a guess, because now the only way, once we have decided to make P false, to make this clause true, is to make Q true. And now we get run into a conflict, right, with a clause P or not Q. This is exactly the same as DPLL. Now, what DPLL would do now is to backtrack and say, okay, this cannot be the case. What we do in CDCL is we also backtrack, this cannot be the case, but we learn something, right? We learn from the conflict between the propagation P or Q from the Q and the false clause P or not Q. So we can show that whenever such a situation arises, that we propagate a propositional variable like the Q here and run into a conflict, then we can learn a new clause that actually advances what we know about the problem. Now, in this case, this is a pretty strong clause. It's a unit, right? We can combine P or not Q and P or Q to P. And now we add this clause actually to the set of clauses, to our conjunct. Now, in this case, as said, this is very, very strong. So actually, if we add P, when we can throw away P or Q and P or not Q, because P implies already the truth of P or not Q and P or Q. And even further, we know that because P is true, in order to make this clause true, R must be true. So actually, we can reduce the overall thing to R and P. And if you look into the truth table, right, these are exactly the two rows here where this formula becomes true, where R and P are true, right? And Q doesn't matter. Okay, so what the algorithm will do here now, it will backtrack, right? And learn the new clause P. And now this is no longer guessed, but because we learned the clause, it's justified by P. It will then learn the R from the second clause here, and we are done and we have the same result. Okay. And so what we combine here now is resolution and this enumeration of possible valuations. And it turns out that this combination has a lot of benefits. And actually in practice, it turns both algorithms that were not very successful on that, resolution is not successful at all, DPLL was better than truth tables, but still far away from able to solve something in the real world, right? We turn it into something that really works. Okay. Now, why does this work now? And this is something I looked into some years ago. And one very important difference to solely applying resolution is if you generate clauses, resolution inferences will weigh by looking only into inferences that come out of a false clause because of a valuation assumption and something that propagates, then you can say that all these newly declared clauses with weight are not redundant. So what does redundant mean here? For example, what I've shown you before, if you do a resolution set between not P or Q and P or not Q, you derive a tautology. Tautology are redundant, right? So you will never ever be able to derive a tautology that way, right? Why? Now, for example, if you would make P true here, right, then you would immediately propagate Q, and the second clause would also be true, and you would not make an inference at all. You would immediately find a satisfying assignment. Okay. So what you can show is that no tautologies, existing clauses are learned, but even more. Actually, what you can show is non-redundancy means you will not learn anything that is implied by smaller clauses. Okay, so you can use the ordering of the literals on the model assumption, like with PQ stuff we have seen before, order the clauses that way, lift these two clauses, and then you can show whatever you will learn here is not implied by smaller clauses from your clause set. And this test whether something is redundant with respect to smaller clauses actually as hard as the original problem. So it's a little bit like in cryptography, right? Where you can encode something very efficiently, but decoding cannot be efficiently done. Here is even stronger because you can actually prove that this non-redundancy criterion is as hard as the original one. Having an arbitrary clause testing whether it's non-redundant is NP hard as well. However, generating learned clauses can be done in polynomial time. Right. And yeah, for SAT or for satisfiability, this non-redundancy criterion already implies termination, right? Because if you don't learn duplicate clauses, there are only finitely many clauses, you know that your algorithm will already terminate because you only learn non-redundant stuff. Good. So learning new clauses is actually essential to solve hard problems. And just to give you one more example, so this is one of the classic examples from the paper I mentioned before from 1979. If you look into these 4 clauses here, right, then if you do truth tables or DPLL, you will in general need exponentially many steps to show that it's unsatisfiable. However, with CDCL, already linear steps will suffice to show that it is unsatisfiable. For example, when this is a completely symmetric problem in A and B, right? If you make A true, you can immediately infer here B. You can immediately infer here not B. That means we will learn not A. That's one step. And with not A, you immediately run in a conflict because with not A, you imply B, and not B, and you are done. Right? So it's really a linear chain for any type of these problems that you just follow and figure out that things are unsatisfiable. Whereas if you do the DPLL style or truth table style, you will really have to look into exponentially many evaluations. Okay, another observation is that I showed you before, or I argued before, that you can learn more than 2 to the power of n clauses, and actually you can show that this really happens. You can construct easily, it's not maybe not easily, but you can construct examples where you learn more than 2 to the n power number of clauses. However, if you do it with CDCL approach, you only do the resolution steps between clauses you found false with respect to your evaluation. Then you can show that you learn at most 2 to the power of n clauses, right? You can also, that means you can also show that this disadvantage of the resolution in general, that you can learn more clauses when there are evaluations, will disappear. Yeah? You will only learn at most 2 to the power of n clauses. Okay, still, there is of course an issue, right? Because we have still the issue that we learn many clauses. And if you look at today's computer architectures, at least the classical ones, and just a side remark, it's only a few years ago that people were able to have algorithms running on GPUs that are sometimes, I say sometimes, faster than algorithms running on classical CPU hardware, right? You have this memory issue, right? So on today's hardware, you have several layers of caches, right? For example, 2 layers that are on the CPU, when one that is very close to the CPU, and then your main memory. And the speed difference between all these different layers is typically something like a factor of 100. That means if you want to algorithm to run fast, there are a number of things you would like to achieve. One is ideally you would have all your data in the caches that are on the CPU, right? And for sure, this will not work if you learn 2 to the power of n clauses, right? Or in level 3 cache, or but please not on main memory, right? And that means if you naively learn all the 2 to the power of n clauses, still you will have an algorithm that is much better than CDCL, than DPLL or truth tables or resolution, but still also this algorithm will not be able to solve, for example, the Sudokus that fast or any real world problems. You need more. And I will only show you one further technique that is very, very important in this context. And this is actually about throwing away clauses, right? It is a very deep insight, like we throw away information every night, right? This is more or less well known, right? So our brain clears information every night, possibly through dreaming, right? Also, we solvers have to throw clauses away. And it was really an open question for 10 to 15 years how we should do this. And the currently accepted solution to this is was developed by a French group around 2009. And the idea is to say, okay, I only want to throw away clauses that do not contribute to the problem anymore or are of a low quality with respect to the problem. And the striking idea, what quality means here is you simply count the number of decisions, the number of guesses when you do the valuation that you need in order to falsify the clause. Okay, and this was called actually LBD, literal block distance. So let me give you an example. So again, we have our beautiful clauses we have seen before. And then the block distance for P or Q and P or not Q is 1. Why? Now assume you guess not P, then you can propagate Q. So you need only one guessing, only one decision to make this clause false. And the same for the other clause, right? However, for example, for not P or R, if you decide P, right, then you still need to decide not R to make this clause false. So this has literal block distance 2. Okay. Now computing this literal block distance is actually a difficult task, right, in general. So what one does is one uses actually an approximation. Because if you want to really compute the literal block distance, you have to some extent consider many, many evaluations, yeah, depending on which literal you start deciding something. So what one does in practice is when one learns a new clause, one simply looks at the sequence of valuations that you currently have, the sequence of literals you currently have, and then just with respect to this one valuation, with one sequence of literals, you look at how many decisions were needed to make this clause false. This is an approximation, but this approximation has a nice advantage. Firstly, that you get it for free because valuation is already there when you learn the clause. And the second important advantage is that practically it turns out that it works very, very well. Okay. So this says something about the quality of clauses. And then the second question is which clauses should we throw away or how many should we throw away, right? And what typical SAT solvers do today is, and actually these numbers here are one of the most powerful SAT solvers from a French group called Glucose. And what we typically do is that we very, very greedily and eagerly throw away clauses. For example, what we do here, that every 2000 plus 300 times x learned clauses, starting with x equals 1, and x is the number of steps you use to throw away clauses, right? You delete half of the clauses. Yeah, you look at the LBD of the clauses, and you simply throw away half of the clauses. And actually, this makes an incredible difference on the performance of the SAT solver if you add this to your SAT solver. First of all, it makes sure that your memory footprint keeps small for quite a long time, very importantly. But secondly, it turns out that you actually don't need these clauses. This was justified by experiments. So what we have done, we also looked into this with respect to the notion of non-redundancy I've shown you before. So we can, out of this 50% of clauses, something like 50% out of this 50%, so 25 of these clauses are actually also redundant. This is our experience by experiments, but this is still not sufficient to get an efficient solver. So you really need, even if you explicitly remove things that are redundant and you check for that, which means some cost, right? Even if you do that, this is not aggressive enough. You really need this aggressive deletion also of clauses. Okay, so this is really essential for any practically successful solver. Now, what are people doing currently? Yeah, so for example, this is what we are doing. So we try to lift this principle of non-redundant clause learning to more expressive logics, right? So for example, to first order logic, right? And then things get far more complicated because you have to think of instances and things like that. And you get such crazy stuff like factoring and blah, blah, blah. And we also try to lift this to very specific languages. For example, here's a language that we are currently looking into, which is a combination actually of arithmetic, like here x smaller 5, y greater x, and a very simple form of predicate logic where you don't have function symbols. Right, and it turns out that you can nicely use this language to describe simple algorithms that can be used for supervision of systems and technical systems and things like that. Okay, but for all these cases, you can basically lift this non-redundancy principle of CDCL, and also for many cases, in particular for one here that I've shown, you get even something that is decidable. Yeah. What are challenges here? Yeah, the challenge is if you want to lift that and use that in practice is to find appropriate decidable fragments that are first of all, of course, decidable, secondly, have some impact in practice, and also to find efficient reasoning mechanisms. There is one dimension that also shows up as soon as you go beyond propositional logic, and the dimension is that a single inference mechanism like CDCL is not sufficient anymore for robustness. You then need a whole portfolio of different techniques in order to get something that is very, very robust. Okay, and then of course you can also integrate these fragments into more expressive logic via abstraction. Yeah, a little bit like it was done in SMT. Good, let me sum up. So algorithm designed for tractable problems like our sorting or shortest path stuff is mostly analytical. There is no reason or no need to learn anything specific from an instance. Typically, you don't have any dynamic memory requirements. Whereas for hard problems, you typically need a combination of analytical and compositional, right? Analytical, you search for evaluation for SAT. Compositional, you generate new clauses by a resolution, you learn something. And actually, this learning has to be specific for the problem at hand. And you have really to take care of your memory footprint, because if you learn something, it means you have dynamic memory consumption, and then you have to be really, really careful of what you are doing there to get something efficient. And it is even the case that these principles cannot be easily transferred from one logic to the other. You really have to look for any logic, and worst case, even for specific type of problems, into very specific reasoning mechanisms. To give you one example, so almost all hardware producers now use SAT or SAT-related techniques to check their designs. And they have further developed these algorithms for the CPUs or whatever they have there, that they can really use them in a robust way. They know how to cut. Of course, you cannot use the design of an overall processor and then check it via a SAT solver. No way. It's far, far too complex. But we have learned how to break that into pieces, how to put these pieces together, and what type of SAT solvers we actually need for which type of parts of a CPU. And we have learned it in a way that this is now more or less an engineering thing for a new CPU to really check whether the design is okay. So this is the kind of progress that has happened here. Okay, and because of a memory footprint and all that, typical languages where these solvers are implemented are languages where you have really access to the memory, explicit access to the memory, like C or C++. And yeah, a little bit of a warning. Or yeah, so what I've shown you are very important aspects for SAT solving. Yeah, this was doing partial valuations, guiding with that resolution step, forgetting things, but this is only the tip of the iceberg. So if you are really interested in full detail, there is, let me type this here, there is a solver by Armin Biere that is called Caticle. You can Google it. And what Armin did here for the first time, and I think this is very, very nice, he actually, you can look at the code, it's all public, but it's not only the code also has references to the respective papers and explained why something is here and what is the progress you get out of that. So if you're really interested in state-of-the-art SAT solving, have a look there. And yeah, that's all I wanted to say. Thanks for your attention.
Thank you very much, Chris, for an excellent talk. Questions? Because we do have time for them.
Yeah, I have a lot of time.
So there's a question in the chat.
There's a question. Could this study possibly lead to a formal proof of P, NP? Unfortunately not. Or I don't know. No, this cannot lead to a so people that okay, so I'm not an expert in the history of P equals NP or P not equal NP. Maybe Deepak knows much more about this than I. So there was a time many years ago that people tried to attack this problem really through logic, right? Meanwhile, they use different techniques to attack the problem. No, it's not a path for P to NP. Meanwhile, they use big math stuff, in particular on graph structures, to try to find a path to show actually that P is different from NP, right? So nobody believes that this is really equal. All right, but no, this is just practical considerations.
So if I can add a comment to Chris's comment, Donald Knuth, who I think every computer scientist should know him. He's the granddaddy of algorithms. Because of all this progress that Chris was alluding to in CDCL and SAT solving, it made him rethink whether P is not equal to NP. And now in an interview that he gave about 5 or 6 years ago, he thinks that maybe P is equal to NP, but then the polynomial degree of the polynomial that will be used for solving NP hard problems will be very, very high.
Okay. I don't know. So we have some people in Saarbruecken that work on this, and not directly, but to problems related, and they all believe in that it's different. But anyway, yeah, let's see. Maybe we will.
Have you read, Chris? Have you read the Knuth's interview? You should read it if you haven't.
Yeah, I will go. Will I find it on the internet?
I think so.
Okay, yes, I would love to read that one. Yeah, this is also a nice remark by Deepak, because as Deepak told, I mean, Knuth started actually in logic and then went to algorithms, and for a long time he was also one of the guys that was thinking it does not make much sense to study problems that are NP hard, like SAT solving. And then with all the progress in SAT solving, he changed his mind now in his encyclopedia, there is even a chapter, book, section, or whatever you call it on SAT solving.
Yep.
Which is very, very densely written, very, very nicely done. And actually he invited all the top SAT people for many weeks to his home and so on to make this work. This is really a beautiful story. But I didn't know, Deepak, that he now even believes that it could be, that P could equal P.
So that's the remark he gives in his interview. It's a long interview about his life and his career. But one of the remarks is that maybe P is equal to NP, but the polynomial degree of the polynomial for NP hard problems may be very, very high. So for all practical purposes, P is not equal to NP.
Yeah.
Other question? There's another question? Okay, no. It says thank you. So let me ask you a question. We'll wait for some students to come up with questions. Basically, so when you try to take these ideas to first order logic, what are the difficulties you face?
Oh, there are many difficulties. You get difficulties everywhere. So it took us actually several years. I mean, it's not to find the right strategy and the right. So in propositional logic, okay, let's go back. So one aspect is if you have a valuation in propositional logic, it has at most size n, right? Because you assign to each variable truth value, and there are only n variables, and n is very small with respect to the set of clauses you're typically considering. So there's no issue. You try to assign really truth values to these n different variables, and then you see what will happen. Now, in first order logic, this corresponds to the number of groundings you could have with respect to a clause set, and there are infinitely many in general. So that's the first issue that you have. It even turns out that even if you can limit this to a finite number, this number can easily be exponential, also in practice. And you cannot afford doing always exponentially many propagations or valuations. So one of the very important things you have to solve is to, on one hand, restrict really the number of propagations and things like that, but still guarantee that whatever you learn, what you derive, is non-redundant. And it took us a while to solve this one. So this one is meanwhile solved. We have not implemented anything to this. So we are currently really implementing the first solvers on this principle. So we don't know how well it will work in practice actually on such problems. And it has also many consequences on data structures. So data structures, as you know them from propositional or even first order logic solvers, get far more complicated. Yeah. Are there any other hard problems that cannot be solved with this method? Yeah, there are many. This is really funny. Yeah, this is a very good question. So this is really funny because, for example, if we are in this hardware world, right, it's billions of clauses and millions of variables, and people know how to solve that. It's very easy to write a problem. That's not maybe not very easy, but it's not too difficult to write a problem with some 300 or 400 variables no solver can solve. Let me give you an example. Let me give you a little bit of an example. For example, you might know that how matrix multiplication works, right? You have two matrices and you want to multiply them, okay? And the standard algorithms needs n to the power of 3 multiplications, right? When many years ago, there were people that figured out, oh, if you do not do this naively, but you do the right products, then actually you can get down from this n to the power of 3 to something less. I don't want to go into details, okay? And it's an open challenge to improve this. And of course, if you can improve this, this has an incredible effect on various branches on computer science if you can speed up matrix multiplication. Now, one of these problems you can encode in propositional logic, where basically you say, my propositional problem encodes all the ways you potentially could build multiplications and additions to do a certain matrix multiplication. These problems have around 2,000 variables and something like 8 to 10,000 clauses, so they are really small compared to this hardware stuff. And it's an open problem still for many years. And when many groups in the world that try to attack these problems with SOT solvers, including ours, we also spent half a year on this one. We haven't managed to do that, right? So there are really interesting and also pretty small problems that cannot yet be solved by this technology.
Let me add another comment. You must have seen a recent announcement of a recent paper on matrix multiplication, where basically they use Strassen's algorithm for reducing matrix multiplication of, say, n by n matrices to blocks of 3 by 3 matrices, and then down to 2 by 2 matrices. So there is some, I'm trying to remember the name of the company, DeepL or something like that.
Could be, yeah.
Yeah, they use the learning techniques to find the most efficient way of doing 2 by 2 multiplication of 2 by 2 matrices.
Yeah.
Either 2 by 2 or 3 by 3.
Then for particular examples, example driven or?
No. So
okay.
basically they can reduce the number of multiplications from, I forget the details, from some 7 to say 6 or 6 to 5.
So for 3 times 3, I think the challenge is to get below 21, if I remember correctly. So one of our colleagues in Saarbruecken has proved that the lower bound is 19. You cannot do it with 19.
I see.
With some deep math in, but between 19 and 21 there is this gap. For
so
2 by 2,
3 by 3 matrices.
Yeah, this by 3 by 3.
I see.
And 2 by 2, I didn't know, but yeah, it sounds very interesting.
I will also send you the link. There was an article write up on that in Quanta magazine.
Okay, that would be good.
Yeah.
Okay, let me ask over two more questions. Are heuristic motivated from real problems or from decided logic problems? Yeah, of course, propositional logic, yeah, it could be both ways, right? Propositional logic is decidable, of course, and then for propositional logic, one really tries to solve real world problems and then finds heuristics. And it's really the case that heuristics are also specific to real world problems. The hardware people have completely different heuristics than the people where you use a SAT solver, for example, at the very bottom of a model checker. Yeah, and if you, as soon as you move to more expressive logics, then of course decidable fragments play a big role. Yeah, this is one thing. Similar to this, we have, for example, information theoretic measures being considered to be used to determine which result to discard. Ah, you mean throwing away clauses? Yeah, there is one way to throw away clauses which I mentioned, not in all technical detail, and this is what I called redundant. Yeah, you can throw away redundant clauses. So actually, we have our own SAT solvers, and where we do that. So this was actually one of my motivations to build our own software, because nobody else has done this before. I was very curious what will happen if I throw away redundant clauses first, before using any heuristic of throwing away clauses. Unfortunately, the answer is yes, it helps a little bit, but it also is quite costly. So at the end of the day, throwing away clauses via heuristic is far more efficient and far more effective. And the reason is actually what I have shown you. Assume you throw by accident away a clause, yeah, a clause that is important for some extent. Then you will probably learn it again. But learning a new clause is not a big thing. On the other hand, if you throw for something away that is redundant, you will not learn it again, because we have this theoretic result. Whatever you learn will not be redundant. So we can actually view of this heuristic throwing away things as a very efficient way of throwing away redundant clauses. And this is really how it is in practice, unfortunately, if you believe in throwing away redundant things like I do. Yeah.
Other questions, please. Well, there don't seem to be any more questions. Thank you very much, Chris.
Yeah, thank you for inviting. Yeah, I should say let me just say at the very end, I know that Deepak mentioned that I know him for many, many years, but what he didn't mention is that he always was also an advisor of me, and that we had many, many discussions, and I learned a lot from Deepak, and I would not be here without Deepak, I would say, right? So thanks a lot, Deepak.
You have been very generous. Thank you very much.
Okay.
Thank you, and good night, man.
Yeah, good night. Have a nice day.
Bye.
Bye-bye.